Okay, welcome to WASA Distance Education. This is MBF3C, grade 11 college prep math. I'm Keith, I'm your teacher, and we're midway through uh, um, our study of trigonometry, and today we're going to take a look at a different way of approaching triangles. Up till now, we've looked at triangles, and in order to solve a triangle, you either had to have a right triangle, right? So you had to have a right angle triangle, or in some cases, you may have had some regular triangle, and then you kind of had to do a strange thing where you turned it into two right triangles or something like that. Okay. Now, there is a way, a fairly straightforward way to solve certain items from, oops, sec. Try that again. Okay. Sorry, just had a little problem there. Yeah, there's a way to solve triangles that are missing items that aren't right angled. Okay, and there's a couple of ways we're going to look at doing it. We're going to look at the law of sines right now, and then we will next week we'll spend a little time on that. Next week we're going to look at the law of cosines. Now the law of sines isn't much more complicated than the trig identities, the SOHCAHTOA that we've been looking at. But remember that the law of sines actually applies to any triangle, except it doesn't really apply to right triangles. You can use it on right triangles, but what'll happen is you're better off using the trig identities, right? The SOHCAHTOA. So a right triangle. All right. So for a right triangle, you're going to use SOHCAHTOA. And then for other triangles, see, it's a little triangle symbol with an S on it. You're going to use the law of sines. Okay. And then we're also going to look at the law of cosines. Okay. Now, it's called the law of sines. It's also called the sine law. Unfortunately, our text kind of flips between them, and I call it the sine law, actually. So we'll just kind of understand it's just called the sine law or the law of sine. Doesn't really matter. So the sine law basically is a ratio. And you're going to see, it's going to look a little strange at first because it's going to give you three fractions for a ratio. But actually, we're usually only going to use two of them to solve a problem with a triangle. So let's take a look at this triangle. This is triangle A, B, C right here. Okay, and then of course the opposite sides are little a, little b, and little c. They're written there in the book on page 21, but it's really not that obvious. They're kind of small letters. So what the sine law is just a ratio between the sine of an angle and the length of its opposite side. Okay, this is just a kind of a true statement for any triangle, that the length of the side and the sine of the angle have a constant relationship between each angle and each opposite side in a triangle. So the sine of A, which is right here, and the divided by its opposite side is the same number as the sine of B and the length of its opposite side, and so on, right? Sine C. Now, the sine law, because it's a ratio, and remember that equal sign means that if we do something to one side of the equal sign, we can do the same thing to the other side, and it won't change the equality. So I could take the reciprocal, I could flip these fractions upside down, and that's where the or part comes in. Now, the reason you're going to pick that is if you're unknown, if you're trying to find the sine of A, then you're going to pick this format because you want to have the unknown in the numerator. And if you're trying to find A, the side length, then you want to pick that format. It just makes it easier when you're it saves you a step when you're trying to isolate the variable. Okay, so here's where you can use the sine law. Okay, now you don't really have to memorize this because uh, basically you're gonna um, if you try to write out the sine law and you don't have enough information, then you're not going to be able to do it. So you'll know right away. But basically, you need two sides and an angle, or two angles and a side. That's it. That's really right. And if you have two sides and an angle, then you're going to be able to find the second angle. And if you have two angles and a side, then you're going to be able to find the missing side. Okay, that's what you can do with the sine law. So there are some cases you won't be able to solve with the sine law, and if you're kind of thinking a little bit ahead, because I mentioned that there is a cosine law as well, and if indeed the cosine law is our kryptonite here as far as solving triangles, because that's it. You get to you get to a certain step, and if you can't use SOHCAHTOA and you can't use the sine law, then you break out the cosine law, and you can solve any triangle. So they say they tell you what you need here, but you'll be able to figure it out, I think. All right, well let's take a look at how this works. It probably looks more complicated than it really is. Oh yeah, okay. They're still telling you what you need here. Okay. All right, here we go. The best way to learn this is to follow the examples. If you follow along with these examples yourself and just try and work your way through them, to me, that probably teaches you more than trying to read the text. So it says, find the missing side is indicated using the law of sine or the sine law or whatever you want to call it. So the missing side here is x, and this is 8. Let's call it meters. Remember that everything we do in geometry, trigonometry, has a measurement with it, just except for ratios, unitless ratios, but just about everything else does. So let's keep going with that by including units. So now we have two angles here, and so they've called it x. But what we're going to say then is that x divided by the sine of the side opposite x. So here's x, and we want to find the angle that doesn't touch that side. Okay? Well, you see the 24 touches that side x up here. Okay, and this angle, which doesn't even have a measure, but we could figure it out. It touches x on the other side. The only angle it doesn't touch x is this right here. So that's the one we want. We want the angle that's opposite the side. And then we're going to say the sine, in this case, 39 degrees. Okay, so there you go. So x over sine 39 degrees equals, and now all we need is another side and an angle. And what we need is a side and an angle that are opposite each other. So that's the important piece. If we didn't have that, we'd be stuck at this point. Okay, we'd have to break out the kryptonite, and we have to wait until next lesson, Monday, before we see how that one works. But anyway, fortunately here we have, you see, we have the 24 degrees, and then we have the 8 meters. So we have an angle and a side opposite. So what are we putting in the numerator? We're putting the sides in the numerator in this case. So let's go put our 8 meters up there. And then we're putting the sines in the denominator. Okay, we have a choice. As long as we're consistent, it doesn't matter. You can put the sides in the top and the sines in the bottom, or you can put the sines in the top and the sides in the bottom, as long as we're consistent. So this is going to be the sine of 24 degrees. Okay. There we are. Look at that. So we now have a ratio, and this is really, to me, this is a thing of beauty right here. Look at this. We have a equation, and there's only one unknown, right? So we just pull out our algebra skills at this point, and we can solve this equation. Okay. Now the easiest way to isolate x, because x is in the numerator, okay, because it's already up on the top there, all we really have to do is get rid of that sine 39 degrees. So the easiest way to do that is multiply both sides by sine 39 degrees. And the net effect of that is to sine 39 degrees, and then it's times 8 meters over sine 24 degrees. There you go. Okay. Now, you can put the sine 39 on the other side. You could write it up here. It really doesn't matter because the sine 39 degrees works out to a number. So it's just the same. It's putting a constant there. Okay. So you'll see that formatted in different ways. As a matter of fact, yeah, let's see, what do they do in the text here? Yeah, so they format it this way, right? Which is exactly the same thing. I know it doesn't look like it, but just to show you why they're able to show it this way down here, that's basically sine 39 degrees over 1, right? That's what that really means. And so if we wanted to simplify that, we'd have 8 times sine 39 degrees, and then 1 times sine 24. Sine 24 degrees. Okay, so that's how they ended up with that. And it's just a different style of showing what's going on. The way I show it there is perfectly fine for me because at this point, I'm just going to go and solve this because I have everything I need on the on the right hand side to solve that. Okay. Now, just before I do solve it, let's say that you wrote this out and somehow you had sine 39 degrees over x equals sine 24 degrees over 8. Let's say you had it that way just because maybe you were writing things down and weren't really sure what the unknown was. That's fine. That happens sometimes, and there's no problem there. All you do is just in your next step, you take the reciprocal of both sides. You flip the fractions over on both sides, and you end up with that very next line that I started with, right? And you're allowed to do that. There's nothing dodgy about it, right? And if you think there's something dodgy about it, try it. If you have a 2 equals 2, and the reciprocal of 2 is 1 over 2, right? And if you take the reciprocal of 2 on both sides of an equal sign, you're going to have a half on both sides. Well, a half is still equal to a half. It's still an equality. It's still correct. Okay, so that's what we're talking about here. All right, so we have our x, and now we just have to work out 8 times sine 39 divided by sine 24. So 8 times sine 39, make sure you're in degrees, divided by sine 24. Okay, and now we have 12 point. Let's round it off, and don't forget your units. They are not putting the units in the text, and it's a little bit. They should. It's just a little oversight. Okay. So there. So now, what does this mean? Let's go back to our diagram here, and write in. It's what the answer? 12.4. 12.4 meters. So we can write that in. And I strongly recommend you do that. Get in the habit of doing that as you're solving these triangles. Anything that you calculate, you write it on your diagram. Right? Any new information that's given to you that's not already on the diagram in the description, write it on your diagram. Try and distinguish between what you've calculated and what you've worked out from the question. In this case, there was no extra information, but sometimes they'll tell you how long a side is or what an angle is in the words. So if you get used to going back and educating your diagram, adding information to it, then it'll really help you as you're doing these more complex problems. Because the diagram, I think, is one of the keys to being able to solve these. You get a good diagram. From the good diagram, you can pick which law, which rules, which formulas apply. And once you have that set up, you're done, really. It's just a matter of manipulating things and solving the resulting equation. Okay. So let's take a look at the next example. Okay, so in the last example, we were asked to find an unknown side. Now, it looks like they're going to ask us to find an unknown angle, capital X. Maybe I wouldn't pick that, but at least this one they have units. Okay, so we're still going to be able to use the law of sines. Let's use the law of sines in this case, because it's an angle. Let's use the one that has the sign on top. So the sine of x, now we need to know the side opposite x, how long it is. Now, if we tried that right now and there was no side opposite x, we'd be done. Okay, we would have to wait until chapter 12, lesson 12. But fortunately, we have the opposite side. But that's the problem with the law of sines. If we didn't have the opposite side, we have no way to calculate that. We do if we have two angles in a triangle and we need the third angle. We can actually work that out using the sum of the interior angles of a triangle being equal to 180 degrees. So there's some things we can fix. If we're missing an angle, we already have two, we can fix that. But if we're missing a side, the law of sines isn't going to help us. All right. So sine x over 9.2 centimeters. So now we have an angle and its opposite side. And now all we need is one more angle and its opposite side. And z comes to the rescue here. So it's sine 84 degrees. Don't forget the degree sign because it is a measurement. Okay, 116, no, 11.6 centimeters. That decimal place is really tiny, but all right, well, there we go. Now, if we look at this equation, we see that we have three knowns and one unknown, and that's usually a solvable equation for us. So let's apply our our algebra skills now. We've got to get rid of this 9.2 underneath the sine x, and we can actually do that. The book's going to show you a couple extra steps, but basically we're going to take this and we're just going to move it up either here or up there, and it doesn't matter which way you do it. It works out to be the same thing. Just because of the way I learn my math, I'm going to put the 9.2, and we know it's centimeters, 84 degrees over 11.6. Actually, let me just put the centimeters in. It's kind of, because I'll show you what happens here, is that the centimeters cancel out, and then the only unit we're left with is degrees, which makes sense because that's what we're trying to do. We're trying to find an angle in degrees. Okay, so now that we have this, we need to be able to figure out what angle x is, and we're going to end up with a number when we work this right-hand side out. And what we can do is, if you remember, the way to find the angle from a ratio is to use the inverse sine. So I'll just work out what we have on the left side, the right side there. It's not always strictly necessary that you have to show that because it's a big, long number. But, if you're not real sure, just go ahead and show it because it gives me something to work with if you're having problems. So 0.7887 59. I'm just rounding it off to 6 decimal places. And then if we take the inverse sign of that, which is usually your above your sign button, it'll be printed in a different color. And okay, and then I basically get 52. It's 52.1 degrees. Kind of hard to say. 52.1 degrees. We say approximately. I'll use those wavy equal sign. Now, they were only giving us angles to 1 to the nearest degree. They were giving us measurements to 1 decimal place. So I think probably 1 decimal place, probably good. Okay. Yeah, they're showing here, press the second function and then the sign key. Okay, very often it's called second to ND on your calculator, but sometimes they call it FN for function. There's different calculators have different ways of accessing the inverse sine function. And your iPhone has that function too. You just have to turn it into a scientific calculator by turning it sideways. Okay. So there you go. So your angle x then is about 52.1 degrees or 52 degrees. Okay. So we used the law of sine to find a missing angle. Okay, we had, and that's a good use of that because you see our little trick. If we had two angles, then this is 51.1 degrees right there. If we had two angles, then we could find out the third one without too much more trouble. For example, right now we could find out y just by subtracting the two knowns from 180, and what's left over is going to be our angle y in degrees. Okay, and since we have y, then we could go ahead if we really wanted to and work out little y, side little y. So we could actually figure out everything about this triangle just from the information we generated from this question. Okay. All right, now, all right, let's take a look here at some of the support questions, and yeah, we'll just try some of those. So, okay, so given each of the ratios below, state whether the unknown angle will be larger or smaller than the one given. Okay, well, I'll keeping in mind that these numbers are supposed to be, the ratios are supposed to be about the same. Okay, so sine 67 degrees divided by 13 should be exactly the same as 7.2 sine x, right? So the way I look at something like this is that the ratio is the same, but in this case we're probably dividing by 2, right? We have to divide that numerator by 2 in order to get to 7 point, approximately 2. It's actually um, a little less than 2, something like that, like 1.9 or something. So then that's in order to make this ratio the same. So what do you think the angle would be, right? Because remember the 7.2 divides into this angle, so that number, that x, sine x, sorry, has to be about twice as big as this sine 67. Right? These are really tricky questions, to be honest with you. Anyway, I'm gonna let you work at that. Now, of course, the 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 answer you could do is just work out what the x is, and then you can get an idea. But try and figure it out, um, whether it's bigger or smaller first, and then see if you're right by checking with the sine x, uh, solving for sine x. Okay, and then the same thing over here, question 2. Okay, let's go ahead and solve some of these problems here. Find the length of the indicated side. So they're giving us a triangle with a couple of angles. Now the thing I want to point out is that they don't always draw these triangles to scale. That's a generic triangle. And I can tell that because you see that angle of 99 degrees. I don't think that that's really a 99 degree angle. It could be, but probably not. So don't look at the triangle and say, oh, it's a very small angle and it's got to be a small number. No, they just draw some random triangle and put some numbers in. Okay. Okay, so how are we going to solve this one? I think there's room right here to solve this one. I might have to go to a new page to solve the next one. So we're going to solve x, and let's see if we can do this. In order to solve x, we need the angle opposite x, which we have. Okay, and we need another angle and another side. And we have a little wee bit of a problem here because you see this one, we don't have that side. Okay, and we have this side, but we don't have that angle right there, right? Now, of those two pieces of missing information, if we had one of them, we could proceed. But of those pieces of missing information, we actually can't. This one we can't work out at all. We can't work out the side. Right? We could if we had x. We don't have x yet. But once we get x, we could then go ahead and work out that other side. But what we can work out right now is this angle right here. Right? We know what this angle is. This angle, let's call it, I don't know what we're going to call it. Let's call it A. Okay? So angle A is equal to 180 degrees minus 99 degrees minus 54 degrees. So the thing about this grade 11 math, college prep math here, is that they're not just giving you straight up, giving you everything you need. In some cases, they're asking you to work a little bit and use some other stuff that you may know to solve the problem. So we have 180 minus 99 minus 54, and I end up with 27 degrees, right? So A is 27 degrees. Okay. Well, now I'm going to use blue here. Actually, I keep using red. Now I have it degrees for angle A, and I have the opposite side. So I have everything I need to solve using the law of sines, I think. Anyway, let's set it up. Okay, and that's the other thing about math, right? We're in really step 1 and 2 of the 4-step problem solving model. The first step is to understand the problem. So what I understood there is that we needed a bit of additional information. Step 2 is to develop a plan for solving the problem. So my plan was we need that missing angle, and then we're going to use the law of sines. That's my plan. And then step 3 is implement your plan. Well, we all know that plans don't always go according to plan. We all know that things can, maybe I overlooked something. Maybe I didn't quite understand the problem. So if I set this up and I don't have enough information, no problem. We'll figure something else out. We'll go back to step 2, maybe even to step 1, make sure I understood the problem. Okay, so we're on step 3 of the 4-step problem solving model. So let's try it. We need x, so let's put x above on top. And then the angle opposite x is 54, so it's a sine 54 degrees. So far, so good. Okay, and now we need another angle on another side. So I said that we could use A, and so we need the 8 centimeters over here. And then it's a sine of 27 degrees. Okay, now I'm looking at that and I'm thinking, I think I have everything I need. Okay, so I should be ready to go here. Okay, and now x is a side length, so we're really just gonna let's see, it's sine. How are we gonna? It's gonna be 8 centimeters, sine 54 degrees, and all of that over the sine of 27 degrees. Okay, yeah, there you go. And now, just before I run out of room here, what's x going to be? X equals, and it's going to be a length in centimeters, because that's the units we're using. So it's 8, whoops, 8 times the sine of 54 divided by the sine of 27. Okay, and so I get 14.3 centimeters. That's it, 14.3 centimeters. Now, if you solve that problem and you're not real sure, you can always look it up in the back, the support question answers. So we're lesson 12, support question 3, and you can see it there, it's 14.3. They got the same thing as I did. As a matter of fact, they have they have a solution there, but the only thing that they don't show you where they got the 27 degrees. Okay, so in their solution, they didn't show you this part right up here. Okay, so that's how you go about solving some of these. So for question 4, let's take a look at what we got here. I'm going to have to make a new page because there's just really no room to cram this in. So for question 4, it says find the measure of angle A. So there's angle A right there. We have the side opposite, so that looks good. Oh, and look, we have an angle and a side opposite. So this one's just straight up just applying the law of sines. There's nothing really to work out first, right? So let's just go ahead and do that. I'm going to grab, just going to make a new page here. Okay, so you can keep working on this. This is a support question. Okay, I just, okay. This is support question 4. Yeah, support question 4, page 24. And so the diagram, I'm just going to model for you how to do the diagrams in the sense that, you can use a ruler if you want to make it look nice. Don't waste a lot of time on your diagrams. Spend your time making sure you get them right. Now, if your writing's too big to fit the angle actually in the angle, you can always just you could do it this way. Just do a little line into the angle and just write it below. Okay, that's the way to show it if you can't fit it in your diagram. Maybe your writing's big. Okay, so there you go. So that's our our situation, and we're being asked to find A. So that's what we want to find. So we can say sine A over the opposite, so it's a 6.7 centimeters equals, now all we need is another angle and its opposite side, and we already have that, the sine of 26 degrees over 3.2 centimeters. All right, I think we have everything. So we're trying to find sine A, so we're going to multiply both sides by 6.7 centimeters. So sine A equals, 6.7 times sine 26 degrees over 3.2 centimeters. Actually, these are centimeters up here too. I should be consistent. Okay, that looks pretty good. And now I'm just going to work all that out, and we're going to end up with a number, right? Now, this next step, you could actually just say, you could just really go to the final answer once you get some experience with it. But I'm just going to, whoops, S-I-N. Okay, well, that's not looking so hot. Let's try that again. Sine, inverse sine, and I'll just work it through here. So it's 6.7 times sine 26 divided by 3.2, and so I got 0.917 840. That's what it rounds off to at 6 decimal places. Okay. And now I just press the inverse sine button on what I have in my calculator, which is going to be a lot more than 6 decimal places. Most calculators will have about 10 decimal places, or even more that they don't even show you. So I get 66.6 degrees, and that's important that we know that it's in degrees because it's an angle. And yeah, that's what I got. So let's take a look at the answer in the back of the book, and that's part 4. For support question 12. So, oops. Okay, lesson. I'm just finding it here. Okay. So, okay, it's a lot harder to find than it looks. Okay, so question 4, 66.6 degrees. Yeah, so we got that, right? And really, that's how it goes. Okay, let's take a look at the next one. These are support questions. So, in this particular case, I think doing a lot of these support questions will really help you out, help you to understand this concept. And you shouldn't encounter any questions here where you don't have enough information. You might have to calculate the angle, but you should be able to have enough sides to use it. Okay. All right, let's take a look at the 5. So now in the case of support question 5, it's basically telling you a story in words. In triangle PQR, find the value of little q if angle R is 73 degrees, angle Q is 32 degrees, and R is 23 centimeters. So really it's telling you a story. Okay, so let's take a look at how we would go about solving that. So this is a support question 5, and that's on page 24. So triangle PQR. So it's a PQR, and the value of little q, which is over here, it's opposite big Q. Oh, we got to find that. That's the one we want to find. Okay, good. Angle R is 73 degrees, so that's 73 degrees. Make sure my writing's good. Angle Q is 32 degrees, so 32 degrees. And little r is 23 centimeters. R, 23 centimeters. Okay, I think all right, let's see what we have here. So we need to find this one, and we have the angle opposite. That's good. And, oh yeah, okay, we have enough stuff here. We have big R, and we have little r. Okay, so that's all we need. So let's let's write that out. So this is going to be, we're going to put the Q on top. So little, little Q, that's a pretty ugly looking Q. Let's try that again. Okay, so little Q over the sine of 32 degrees, that's that big Q, equals, let's see, 23 centimeters, which is a little r, over top of the sine of 73 degrees, and that's big R. So notice I didn't spend a lot of time drawing my triangle, like with a ruler or anything. You can make the lines look neater, but really all you want is a diagram, and that is something that serves your purpose of organizing your information, right? Really, I'll tell you what, if you're solving these problems and this is the only part of it that you got, you're going to get a mark. Okay, no matter what happens with the rest of it. If you got a good diagram, you're going to get a mark for the question. Okay, usually if something goes horribly wrong, but you got this part right, you'll get another mark for the question. Okay. Unfortunately, if you don't give me a diagram and then something's gone horribly wrong, it's pretty hard to give you very many marks for that question. So it's in your best interest to draw a diagram, just in terms of marks, but it's also, it's a good practice, good habit to be in whenever you're dealing with any kind of geometry, trigonometry, any time whether you need to visualize something and organize information. A diagram is usually the way to go. Okay, let's see. So I think I think we got everything here. Sure, right. We're going to rearrange it so that I know how to write a Q, and it's just going to be the sine of 32 degrees times 23 centimeters over the sine of 73 degrees. Now, you notice I've written it in a different way. It doesn't matter. That's what I'm trying to kind of show you here. This is a style thing, so I can write it that way. If I really wanted to, I could extend this little line here, and I don't know if I can, oops, okay. I was kind of hoping I'd be able to move that, move this little part. No, I can't. It won't let me move that part. Anyway, the point is that it doesn't really matter where you put it, right? Because these numbers, it's like 2 times 3, divided by 6. And it doesn't matter if I write 2 times 3 over 6, right? Or 3 times 2, right? Divided by, it doesn't matter how I organize them. It all comes out to be the same thing mathematically. Okay. So I'll leave you to solve that one. And let's take a look at the next one. I think the next ones are pretty much the same. So, 6, yeah, 6 is going to be like that, and 7. And these are all just good practice. Now, question 9 is interesting. They give you a diagram, which may or may not be good. It's a tiny diagram. I'm not really sure that that's a very useful diagram. The other thing I want to point out is that for some of these questions, and it's unfortunate, but what I've noticed is that sometimes somebody's changed the numbers in the words here, but they didn't change the diagram. So, I'm going to fix that. But in the meantime, I suggest you use the words in the question. But if you don't, if you get it, if you use the diagram, it'll be fine. Okay, but if what they say, yeah, well, here you go. On the ground, the ends of the wire are 17 meters apart. And I think it says 15 there. So you just need to change it to 17. That's exactly, there you go, proves my point. But if you use the 15, I wouldn't mark you wrong for it, obviously. It's just a little glitch in how the editing of this went. Okay, so, but I'm going to get those fixed for next time. So here we are. It's telling us a story, and so let's just make a better diagram. I'm going to start a new page. You can keep watching this, but this is the sort of question that you wouldn't want to have jammed into. Try and jam it into the page. You want a separate sheet of paper. So this is support question 9, and this is page 24 of unit 3. So a radio tower. So here's the tower, Okay. And here's the ground. And it's supported by two wires on opposite sides. So those are called guy wires sometimes, and in some questions they actually call them guy wires. G-U-Y, guy wires. I don't know why they're called guy wires, but that's what they are. Um, they form an angle of 60 degrees at the top of the post. Well, the top of the tower, I think, is what they're trying to say. So 60 degrees. Okay. Now, on the ground, the ends of the wire are 17 meters apart. So I'm just going to change the red to at 17 meters apart. Okay, there you go. So that's basically one side of a triangle, isn't it? Um, um, the ends of the wire, okay, and one wire is at a 45-degree angle to the ground. How long will the wires be? So 45 degrees. Now, here's the thing. They are, um, there's a few questions in the book where you get a similar scenario. And the question is, can you assume that the both sides are equal? Okay? Can you assume that this tower right here is exactly in the middle of the 17, what is it, 17 meters? 17 meter distance there. In some cases, you really can't because of the situation, what it tells you. But in a case like this, let's take a look. Could we solve it without making that assumption? You know what? I think we can solve it without making any assumptions. Okay, we don't know for sure how long this side is. I think we could actually work it out. Yeah, we could work it out. 60 degrees, 45 degrees. I think that we are looking at another, yeah. So this angle over here, just by using the interior angles, we could work it out that that's 45 degrees, but I don't think we need it. If we use the law of sines, we just need to know what one side is, either x or x1 over here. It doesn't really matter. But let's call this side x because we have an angle. See, we have an angle right there. I think we'll be good here. Yeah, we have everything we need. If we want to find the length of this particular guy wire that I've designated with x, let's try it. So x over the sine of 45 degrees, here we are, equals, and now we need another angle on the side, and look at this, we got 17 meters down below, and the sine of 60 degrees. So we didn't really need to make any assumptions. But if we did need to make assumptions, actually, because we're given these measurements, we actually know them. We were able to tell that that is 45 degrees over here, but we don't need it. Okay, now we can solve for x. So x equals, we'll do sine 45 degrees over times 17 meters and divided by sine 60 degrees. There you go. Okay, and I just made a type of mistake that's kind of, yeah, it's kind of amateurish here, but okay, see what I did for the sine 60? I made my degree sign way too big and way too low, and it's fine now, but really, if you came back to this after about a week or so, or if it wasn't you reading it, it was your teacher, that could be bad. It could be sine 600. Okay. All right, you might catch that, but all right, so let's solve for x here. Now, we don't have to take in an inverse sign or anything because we're finding a length, and our length is going to be in meters. So it's just 17 times sine of 45. So sine 45 divided by the sine of 60. Okay, and I get 13.9 meters. There you go. So what were we working out? It was this one right here, 13.9 meters, and that seems to make sense, right? Okay, so but if we wanted to check, we can go as a support question 9, so we can go to the back here for lesson 12, and let's take a look. That's on page 44, and okay, we got 16 point. I got 13.9. I'm wondering sine 60 sine. Okay. Now here's a great example of why I tell you to look in the back of the book with a little grain of salt. The 15 um, on the back there, it's actually 17 in our question. So somebody's changed it. And then, yeah, and because of the 45-degree angle, I think originally there might have been a different angle that was given. And that would change the geometry a little bit. So if you look at the way they worked it out in the back of the book with the 15-meter wide, I don't think they had the same angles. I don't think they were using 60 degrees in that original question. So put a little star beside that and just give yourself a reminder that it's not correct. It's the outline of the solution is correct, but they use different numbers than we do. Okay. So there we go. And you know what? I think we are pretty well, I think we're pretty well gone through all of these. So what I want to do now is I want to go through the key questions, a couple of word questions that students have some, it's just a matter of understanding the question here. So, and because very often it's the first time seeing something like this. So this is the key question on page 25, and you'll notice that as we're going further in the course, the key questions are getting a little shorter. So you'll just be doing a few problems this time around. So there's a couple of them. Let's start at the end here. 10. Does the sine law apply to right triangles? The question you have to ask yourself is, what is the sine of 90 degrees, right? Whoops. So, and what happens when one of your angles is a 90 degree? Because remember that anything that has 90 degrees in the right triangle, the side opposite is going to be the longest side, the hypotenuse. Okay, so anyway, try a few things and see if you can explain that one. Okay, now question 9. An architect designs a house that is 10 meters wide. Okay, so let's try and draw this, because this causes some difficulties. So this is key question 9, and the difficulty is understanding it, partially because I don't know a lot of students know what a rafter is. So it's kind of a bit unfair, isn't it? So the house is 10 meters wide. So we're going to do a side view of the house. There you go. It's 10 meters wide. Okay. And the rafters holding up the roof are equal length and meet at an angle of 65 degrees. The rafters extend 0.4 meters beyond the supporting wall. How long are the rafters? So this is what they're talking about here. And so this is 65 degrees up here. Okay. And I'm going to change to red now. So this is the supporting wall. So we got our triangle. We know that that's 10 meters because that's how wide the house is. And the little extension here is 0.4 meters, right? Okay, so what do we have here? It says that this side and that side are equal length. We have ourselves an equilateral triangle, which means that this angle and that angle are the same, which is good. It means that we can actually find out what those angles are. If I have 180 degrees minus 65 degrees, that's going to tell me what the sum of those two angles are. So 180 minus 65 gives me 115 degrees. So that's the sum of those two angles that I showed you. So 115 degrees divided by 2 gives me 57.5 degrees for each one. I just wrote, yeah, math is a rough draft anyway, so yeah, you can do that perfectly fine. Notice I didn't waste a lot of time erasing stuff, because really we're solving a problem. We got other things to do. Okay, I'm going to change to black, and then I'm going to say, okay, that's 57.5. All right, well, I'll try gold now on the other side here. 57.5 degrees. I don't know what I pushed the wrong button, I guess. Okay, so we know that those two angles are the same because they told us that the rafters are the same length. They told us in the question that these two lines are the same length, which means that the line above the wall, above this red part here, that line and that line are the same length. That's why I was able to to know that the two angles are the same. It's an equilateral triangle, sorry, an isosceles triangle where it has two sides that are the same length. And it's just a rule. When you have two sides that are the same length and the angles opposite the equal sides are the same length. So now we have enough information to find the length of one of these sides. We have enough information to find this length right here, which we can call x. Okay, we're going to use the law of sines, x over, now what's the angle opposite? The sine of 57.5 degrees. How are we doing for time here? Um, Equals, and then we have another angle and a side. It's the 10 meters and the sine of 65 degrees. So we can solve that, but wait, here's the thing. If you stop there, you haven't answered the question. Because if you stop there, you've answered how long this part is here in green. But they want to know how long the rafters are, and the rafters are these pieces of wood that stick out, they jut out past your roof, past the walls of your house. There's a little overhang. And those are 0.4 meters longer than the actual x, right? So you're going to get your answer, x equals whatever, and then you're going to say the rafters are x plus 0.4 meters equals whatever. Okay, so that's what makes this problem a little trickier. Use a diagram and that'll help you out quite a bit. Okay, so that's the law of sines. I had said that we'll spend a little bit of time reviewing this again tomorrow. We might actually be able to get into the law of cosines as well. All right, well let's wrap it up here today then, and we'll